Okay, so for the benefit of our friends who are not with us, I'm recording this so that they can review this later on, and I wanted to review the practice test results. There were mixed results from a number of our classmates, and I've corrected all of them, made comments on all of them. So I encourage everybody to look at their own set of comments that I have sent back to them that show some very minor mistakes in some areas and some very gross mistakes in some other areas. So first thing, recognize this is a series circuit. Recognize that our total in a series circuit is going to be RT equals R1 plus R2 plus R3. In doing so, you want to write down the values very carefully. The first thing you want to do is not just punch things in the calculator. First thing you want to do is you want to make sure you copy. Does it say 780? Did you write 780? Does it say 1.2 kilo? Did you write 1.2 kilo? Does it say 560? Did you write 560? So you're looking at an instructor that does suffer from dyslexia, and I have to double check, triple check what I write down, just to make sure that, yes, everything is written down correctly and it's written in the correct place. My voltage source is 19. I start off with the 19 volt source. So these are your original values. They're given. And you have to check and make sure that you wrote them down correctly, because then you're no longer looking up here, you're looking at your VIR table. You go to add these puppies up, and as long as you recognize to add kilo, then you should end up with 2.54 kilo ohms, okay? Should be hopefully no issue with respect to that. I did see some very interesting challenges in this regard. And here we go, just very quickly go over this. If we use our handy dandy $8.50 calculator, go to add these guys, 780, yes, plus 1.2 exponent what? Kilo is 3. Do I show 780 plus 1.2 kilo? Hit plus, and then the 560. Too fast. 560, way too fast. Come back here, 560, then hit equals. All right, and it does show 2.54 kilo. You check that twice, you make sure you're really happy with it, then you fill in the blank, okay? Don't just take the very first result. Now, this is where some people had some challenges when they went to calculate current. Some of our friends, when they calculated current, you know from Ohm's law, VIR, I is calculated as V over R. Do I have a V of 19 volts? Do I have an R of 2.54 kilo ohms? What some of our classmates did was 19 divide by, and then they punched in 2.54 without the kilo. What happens if we don't put in the kilo? We're going to end up with something that's totally wrong, okay? And some of our friends had some challenges with respect to the engineering, even though they did the calculation correctly. So the calculation should be 19 divided by 2.54 exponent 3. There's your kilo. And then if you hit equals, and it should show 7.48 milli. Some people did calculate this on the calculator correctly. However, they didn't reconcile milli was a lowercase m. I saw several other kinds of engineering prefixes here other than a lowercase m. And if that was written with something other than the lowercase m, that was marked as an error, okay? So you want to make sure that this calculation is in fact correct, that you're confident with it, so you do it again. How long does it take? 19 divided by 2.54 kilo, boom. It's just a few seconds to confirm that you do have 7.48 milli. Then and only then can you fill in this entire column with confidence. Once you do that, then you take this fellow times this in order to get this voltage. Is this number already on our calculator? Go ahead and multiply by 780. This times this. This times this gives you your voltage, and guess what? 5.83, and we get 5.83 volts. So when you go through that, now another interesting thing is once you have that voltage on the display of your calculator, why don't we very quickly calculate power? Because power, P, is equal to I times V. Do we have V on our calculator right now? Yes. Did we have I a moment ago? So we go ahead and multiply what's on the calculator by the I, 7.48. And how do I key in milli? Exponent, change sign, 3. There's your milli. Now if you hit equals, and then you hit engineering, you discover 43.64 milliwatts. And there's my 43.64 milliwatts. And I saw milli P. Somebody wrote down milli P because power, the symbol for power is in fact P, but you don't write down milli P. You write down milliwatts because watts is the unit for power. So I saw some errors there. So the errors that we saw in here that I want to make sure everybody, and let me change this view to speaker view so you can see this in its entirety. Is that more clear for everybody now? Yes. Jacqueline, you had a question?
I do. Will you mark us wrong for a difference of 100th of a decimal place?
Absolutely not.
Okay.
Yeah, no, I understand we're using different calculators, and as we use different calculators, Jacqueline, you and I, we use the TI-84 plus CE, okay, and with this, you and I are constantly scrolling back upstairs to previous values and grabbing those previously calculated values back downstairs and our previously calculated values. Look how many decimal places this is. This is really remarkable. There's a lot of decimal places. And so since our classmates don't have this kind of calculating power, I'm using this for all my calculations. And since our classmates are using our wonderful $8.50 version calculator, marvelous calculator for $8.50, I'm not going to be concerned about answers that are a few hundredths of a decimal place off. Does that answer your question, Jacqueline?
Yes, thank you.
Okay, you're very welcome. I appreciate you asking that. Yay. Now, all right. But the key thing here is not so much the hundredth of the decimal place, are the engineering prefixes. I saw micros in here, and I saw milli P instead of milliwatts, okay, milli Ws, okay? So we got to make sure that we understand our engineering engineer electronic terms as well as our metric prefixes. So we got to have a very good handle on all of that. Now, next, move the camera over to this portion and right here and light this guy up. And this guy was 24.01 kilo ohm. I just saw that on a recalculation. All right, so in this area, some of our friends had some challenges with respect to color coding. Color coding will be part of your test on Monday. You'll have 4-band and 5-band. You'll be calculating minimums and maximums. Expect that, so you should be practicing that. So if we take a look at blue, violet, brown, that converts to 670 plus or minus 10%. So you write down 670 plus or minus 10%. How do you calculate the minimum? You will take the coded value and you will multiply it by what decimal factor for that 10% for minimum. It would be 0.9, yes? And that will calculate to be 6.03 ohms. And by what decimal multiplier do we use to multiply for a maximum? And that should be multiply the coded value by 1.1, and that will calculate to be 737 ohms. Now, my friends, some of our friends calculated the right number, but they transposed the values. I saw 737 for minimum and 603 for maximum. You got to do the calculation correctly to get the correct value, but you also have to write it down on the paper where it's appropriate. So a good case in point, when you're filling out a job application, is your first name John or is your first name Jones? Okay, if you're supposed to be John Jones and Jones is your last name, but what happens if you write your last name in your first name place? Does it make a difference? They're both your names, but you have to write them in the right place. And the same thing here. If I'm looking for minimum, it's got to be written in the minimum space. If I'm looking for maximum, it's got to be written maximum space, not transposed, because that will be counted as an error. Okay. Okay. Next, gray, orange, red. Red tells you got 2 zeros. You got an 8 and a 3 and 2 zeros. So that works out to be, if you punch this into your calculator and let your calculator do the work, your calculator will do the work for you. Clear, clear. So it's 8300, right? And then the moment you hit equals, doesn't it convert to engineering? Because we set this up. Or if it didn't, you could hit the engineering key and you can see 8.3 kilo. And that's what you should be writing down. You should not be writing 8300 ohms plus or minus 10%. Okay, the coded value should be in proper engineering notation. Now, I'll tell you something though, even though that's what we write down on an answer sheet, when you're calculating for minimum at 10%, take the decimal value and multiply that by 0.9. That's easier. So what I'm saying is, if your calculator was clear, it's, for me, it's easier, 8300, 8300 times 0.9, boom, and you get 7.47 kilo. You could also do 8.3 and exponent 3, that's also just as easy, and multiply that by 0.9, and you still get 7.47 kilo, okay? So most of these calculations from our classmates were pretty good. There was no errors in here, except I did see, again, transposing. And so for maximum, again, we take the coded value and we multiply by 1.1, and we will get the 9.13 kilo ohms. All right, now this was very interesting. I did have a number of classmates commit some errors on this particular calculation. So if you look at the three resistors are clearly marked 56 mega, 470 kilo, 150 kilo. So as long as you hit your engineering prefixes properly on your calculator, you will end up with the correct value. So some people had an error here, and I bet you the reason was because they didn't key in these engineering prefixes correctly. I will show you how that's done. Clear. Okay, so it's 56 mega, yeah? So let me raise the calculator. You can see more of what's going on. Here and here. Okay, okay. All right, so let's look at these values. 56 mega. So it will be, clear, 56 exponent, and mega is what power of 10? It's a 6. Now do I have 56 mega? What do I do with that first resistor value if I'm trying to calculate RT in parallel? I have to hit reciprocal, and isn't that our reciprocal key right here? So I tap it. Now I see a -1 here, because that's an X -1. What happens is I'm going to add this to the next one. What's my next one? 470 kilo. So watch this. It's 470, but I have to key in kilo, which is exponent what? 3. What do I have to do after I key in 470 kilo is I have to hit my reciprocal key. There's the X -1 there. And then I have to hit plus. Then there's one more to do, and that one more to do is 150 exponent 3. 3 didn't make it. There it is. And reciprocal, and equals, and reciprocal, and equals. And you notice if we do that correctly, you end up with some power of 10 that's not a multiple of 3. So I have to hit my engineering key, which puts everything in its right place. And guess what we have? 113.48. That 9 makes this a 0.48. So 113.48. What power of 10? Positive 3. So it's 113.48 kilo ohms, yes? Which is what we have here. So as you go through this, you should be practicing these calculations with us as I'm doing them on the calculator now. And the last guide on the bottom of the page, 24.01 kilo, if you key in these values And keep in mind, some people did not key in mega here, and that's what caused the error for the last resistor total for this particular page. So very quickly, what this is if I go to all clear, 45, sorry. So 45 exponent 3 reciprocal plus 115 exponent 3 reciprocal. Oops, I was keying in too fast. Watch my fingers. 145 exponent 3 reciprocal plus 115 exponent 3 reciprocal plus 93.7. Some people forgot the 0.7 exponent 3 for the kilo reciprocal plus, and here's the big one, 15 mega. So it's 15 exponent what for mega? Positive 6. Right there. And you have to reciprocate. Then you hit equals, reciprocate, equals. And you see a 10 power other than a multiple of 3. So what do you need to do? Hit your engineering key. Boom. Works out to be 24.005. What's that 5 in that third digit position cause you to do for the 0.00? Doesn't that cause you to round to be 24.01 kilo? So it should be 24.01 kilo ohms is your total at the bottom of the page. Any questions on that first page at all, my friends? Okay. Let me go on to the second page. Okay, second page. I give you a reiteration for your benefit of your symbols for the electronic quantities, the units for the electronic quantities, the symbol of the units for those electronic quantities, brief definition. Scientists, if you don't have the very first 5 columns put into your journal, you certainly should do so by now, but you probably have many more rows for the other items. Then you also happen to have Ohm's law, which is shown here in these triangles. And the only other thing you're going to need to do any of this is a couple of power formulas, which I've written here and I've written here. All right, let's go through this. 16 volts divided by 1.93 kilo ohms. So if you go to do this very carefully, you should end up with 8.29 milliamps. I did see some other values in here other than what was deemed to be correct. So very quickly, clear. And this would be 16 divided by 1.93. Don't forget that says kilo, so you have to hit exponent 3. So now can you see on the display, 16 divided by 1.93 kilo. Hit equals, and guess what? It automatically lands on a power of 3, so you don't have to change any decimal points. You simply write the answer as 8.29. What? 10 power negative 3? It better say milli. Not milli, milli what? The units for current is amperes, and the symbol for amperes is A. So it has to be lowercase m and a capital A. I did see different prefixes, and I did see different units, and those will be errors, okay? Be very careful there. Here is you're calculating resistance, so resistance is calculated as V divided by I. I have a V, I have an I. The key thing here is entering milliamps correctly. So again, clear. So 53.8, double check, okay? And then you are going to divide by 873.56, and it says milli. So exponent negative 3. Do we have 873.56 milli? Then hit equals. And I don't land on a power that is a multiple of 3, so I have to hit my what? Engineering key. I do so, and guess what? The 61.59. Yes, doesn't the 7 make this 0.58 round to become 0.59? So 61.59, no power of 10, that's a multiple of 3. So it's just whole units, so 61.59 ohms. No milli, no micros, no picos, kilos, nothing, just ohms. That's how that's done. There's a typo in here in the next one. I put a comma. Now, in some parts of the world, a comma is considered a decimal point, but most of you figured it out. That was intended to be a decimal point. And when you go to do this calculation, you're looking for V. Now, according to up here, V is equal to I times R. So we multiply the I times the R. So 15 exponent 3 and multiply by 163.72. Exponent nano is what? And if it doesn't come to you immediately, you do have the magic card in your journals. But with practice, you shouldn't have to think about it. It should be exponent -9. So we hit the negative and we hit the 9. So do I have 163.72 nano? It equals, and the calculation lands on some power multiple of 3. That's a milli. What's this work out to be? 2.46 milli, yeah, not 2.45. Why 2.46? Because that third digit is a 5, which compels us to round this to become 0.46. So there's your 2.46 milli. Everybody okay with that? Then we do have item number 5. You're asked to calculate voltage. Blank is the voltage when you have amps through ohms. Well, voltage, amps, and ohms. What do? Amps is multiplied by ohms. I have amps, I'm going to multiply by ohms. This is straightforward decimal entry, so 0.017. Just make sure you key in and double check what you key in is exactly what you see. Sometimes my finger works too fast and I might miss a digit. It happens to everybody. So just eyeball it, make sure they are the same. And you go ahead and you multiply this by the ohms, 15,000, 15, 3 zeros. So make sure you do show this as 15,000. Look at it. Just because you press the button doesn't mean you automatically keyed it in. Look at the display. If you're happy with the display, hit equals. 10 power of 2, no use to us, hit engineering. And it works out to be 255 whole volts. And that's what you write down. No millis, no micros, nothing, just 255. Any questions on that? Next, the amount of power that a hairdryer requires 9.5 amps of current from 115 volt outlet. Power is equal to I times V. You should have all 4 variations of the power circles in your book. What were the 4 variations? That's 3 variations for power. Right here and right here. So you have P is equal to I times V. P is equal to I squared R, and then V squared PR. So those 3 circles should be written in conjunction with your Ohm's law circle, whether you do this in circle form or VIR, whether you use in circle form or triangular form, should have those handy. And so we're given current, we're given voltage, and we're looking for power. This circle has current, voltage, and you're looking for power. So what do? I multiply the current times the voltage, and I have a current of, clear, 9.5, and I'm going to multiply this by 115 volts. So there's my 9.5 times 115 right there, and hit equals. And lo and behold, I end up with a kilo. And how many kilo? 1.09 kilo. And what are my units of power? Not volts, not ohms. It should be 1.09 kilowatts. Okay? Kilo is a lowercase k, watts is a capital W. Any questions about that? Okay. All right. Then we also happen to have a very nice challenge at the bottom. Not so much of a challenge since you're given the formula right there. They give you the formula that you're going to use. It's one of our circle formulas. P is equal to V squared over R. So do you see from up above that I have P is equal to V squared over R? That's my bottom, my lowermost circle. P would be equal to, put that over there. And do you see V squared over R? And that's what they're citing down here. This. focus. Okay. And move this over here. Cool. Bring calculator in. Nice. All right. So this is what we have. They're giving you a scenario that you have 110 volts at 2.5 ohms. So you write out the formula you're going to use. They suggest that P equals V squared over R. So you write that out. Then you fill in the values. Voltage is 110. And what are we going to do with it? You have to square it. It says square. Some people just wrote down 110 and didn't square it. It says square. You got to square it. And then the R is simply 2.5. So how do we do that on our calculators? Watch, we're going to take 110. And your square key on this handy dandy calculator is right there, x squared. So you hit square. Boom. Does it show 110 with a little superscript 2, which means squared? And what are we going to do? Mathematically, it says we're going to divide. So I'm going to divide by what? 2.5, 2.5. That's what you put into your calculator. The values that you wrote down on paper, based on the formula you wrote down on paper, based on the scenario that told you you're going to use that formula, hit equals. And guess what? It gives you kilo. What kind of kilo? 4.84 kilo. But what are the units of power? It's 4.84 kilowatts. And again, I saw some people write down 4.84 kilo with a capital P. Capital P is a symbol for power, but the units for power is watts. So you have to write down capital W. Then it says, now calculate the power dissipated by the same heater if the generator's output voltage is doubled. They didn't give you a number. They told you in words, it's doubled. Well, what was the voltage before? The generator's output voltage was 110. What's 110 doubled? You multiply it times 2, or you add it to itself. You end up with 220. It's 220 squared divided by 2.5. And again, I had some people do 220 divided by 2.5 and they forgot the squaring. So if you clear the calculator and you take 220 and you square it, x squared right there, boom. And then you divide by 2.5 right there, you will get, boom, and hit engineering because that 10 power 4 does us no good. Hit engineering, 10 power 3, 19.36 kilo. 19.36 kilo ohms, kilo amps, kilowatt, kilowatts. And so what happens is when you double the voltage, what happens to the power? The power quadruples. Because this is 4 times that value. So the power quadrupled. That's very interesting because of the square function in this formula. Any questions on the practice test? Okay, all right. And so I've done a thorough review of the practice test for the benefit of some of our friends who aren't here participating. They can review this in YouTube. I will transfer it sometime over the course of this evening so they can watch it in YouTube. And I encourage everybody to make practice of these calculations so that when we do our test on Monday, and it won't take very long, it won't be 2 pages, it'll probably just be 1 page, but it'll be selected items of different things, and it will be testing your ability to reconcile engineering prefixes. It will be testing your ability to reconcile the proper engineering symbol, the electrical symbol. Is it V? Is it amps? You gotta be proficient with this. This is your new language that you're learning to be proficient with, okay? Okay, all right, I think we're done with this guy. This was very good. Let's move on to some other things. We had a great exercise that you all got credit on last week, and that was building these resistors in parallel. We had 2 resistors in parallel. We added a 3rd resistor in parallel. We added a 4th resistor in parallel. We added a 5th resistor in parallel. And every time you added a resistor, every time you added ohms, the total ohms got less and less and less and less.
Are we also doing a notebook check on Monday?
I'm sorry, you were breaking up, Barbara. I didn't hear your entire question. Could you repeat, please, your question in the chat box for us, please? And that would work out better.
As well.
Yeah, go to the chat right here in the bottom of our screen, and just go ahead and type your question in the chat box, and that way we'll be able to see it and review it. I suspect the question may be, are we building circuits for Monday? And the answer to your question is yes. You have two circuits that you're building for Monday. You have a circuit, what, 9.5 and a circuit 14, I believe. Let's see, I'm not sure why microphone, doesn't matter why microphone isn't working, but you, okay. Are we having a notebook check on Monday as well? Yes, we are having a notebook check on Monday as well. So that's a good reminder to everybody. I would like to check your journals, notebooks, composition books, spiral bound notebooks. Make sure that, you know, before our test, you can use it for Monday. And anything you write in that notebook, you can use. You just can't jam in any papers, any photocopies. The only two things you can put in there, one is the magic card and one is my personal business card. Those are the only two pieces of paper you can add into your journals. Otherwise, everything else is up to you to write out clearly and legibly for your own benefit. So very good question. Thank you very much for asking it. And yes, and so by having your journals checked before the test, it compels you to update your notebook so that they are clear and legible and ready for you to use for your test. You do have two circuits that are part of our week's exercise to build. And let me get to Canvas very quickly. Canvas dashboard, and let's go to our course 50 here. It's asking us to do. I won't play this video except for just the very beginning to make sure everything does work for your benefit. Okay, so it is going 06, 07, 08, 09, good. If I had the sound turned on, then yes, you would be able to hear this, but you can see this, you can play with this. Now their resistor network is a bit more extensive than what I've introduced to you so far. So I will be talking about series parallel circuit reduction in an example in a moment, okay? But you view this is very comprehensive, and go ahead, put a stop on that. Then you had something to build. So let's go ahead, open this particular guy up. And this happens to be shown with a very simple build. You should have these resistors as part of the set that I had given to you. A red, red, brown, a brown, red, brown, and an orange, orange, brown. You should have those, you should measure those, and you should be able to see that we have, and let me make this bigger. It's so small, sorry. Big, 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 big. And big, 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 big. Cool. All right. And, oops, I don't want to mess with it. Don't mess with it. I just want to zoom, zoom, zoom. Cool. Okay, is this big enough for everybody to see on your screens? Okay, so what I'm doing is I'm showing a singular resistor that's tied to the red power rail. From here, this guy's going to come over and it lands on row 17 on the lower side of my dip support groove. And on row 17, remember those 5 holes on each of these rows have continuity with each other. So there is an electrical connection that is happening between this resistor and these other 2. So 3 resistors are connected at one point right here. Then these 2 resistors are going over and into row number 4, it looks like. And so they're connected at row 4, and they're also connected at row 17, along with this first resistor. And at row 4, I happen to have another pin going out. So as you look at this, are you of the agreement that my resistors can be reconciled with this equation, that R total is in fact equal to R1 plus, which means in series, open parentheses, R2 parallel with R3, close parentheses. Is that the electrical relationship that you see that justifies the equation that I've written here? Okay, because this first resistor is R1, and it is in fact in a series single current path to this junction point. And at this junction point, I now have two resistors that are in a parallel current path. Parallel means they have the leads on one side connected to a common point and the leads on the other side connected to a different common point. So these R2 and R3 resistors are in fact in parallel with each other. And then from here, you should be able to reconcile an R total. Now, let's go ahead and decrease my zoom on this. Okay, so it's a VIR, and we're doing this with 4.5 volts. And 4.5 volts, okay. So if you could do this, actually, I'd like to change this. Let's see how many people have any of you actually done this? Jacqueline, have you tried this one yet? Wei Ji, have you tried this?
I have not yet.
Oh, Wei Ji, have you tried this one yet? Okay, I'm going to change this to 5 volts. So, yeah, week number 5. Yeah, let's change this to 5. I had 4.5 from a previous semester because we had 4.5 volt battery packs. We were not using the really cool circuit board power supplies that your group is using. So change this to 5 volts, and I will change it on my documentation. So just make a note of circuit number 14, change the source to 5 volts. So what you'll be doing is you'll be doing a VIR analysis. So there will be 12 cells to fill in here. Save the measurement. Actually, you can measure your R's for now. Actually, you can do it all because you have your own power supplies. You have your own multimeters. So yes, let's see what your current measurements work out to be. So this entire lab, you can do at home, okay? Any questions about the Circuit 14 build assignment? The Circuit 14 build assignment will be to use the 3 of the multiple resistors that I gave you this past week to build into the circuit in this fashion. And you're going to have to move some things around in order to bring in your power supply, all right? So I trust you all will be able to do that. If you have any questions at all about your circuit build, then take a picture of it and shoot it to me in Discord, and I'll be happy to review your circuit build before you put power to it. Is that all right? Okay, if at all you have any apprehension about making current measurements, I would be happy to discuss that with you in Discord before that happens. But why don't we go ahead and try something? I'm going to go ahead and build the circuit very quickly. I have our 5 resistors right there from before. So we're going to do something right now, very similar to this exercise. Let me stop this share. Pull this guy, pull this guy, pull this guy, and we'll just start from scratch. Okay? And I'm going to put in my power supply, make sure I've got space for it, and the power supply will go right there. Make sure I'm not bending any pin. Okay, that snaps in place, that snaps in place. All right, power supply is looking pretty good. All right, so from these resistors, what did I do? I have a brown, red, brown, so I'm not going to use that guy. Red, red, I'm not going to use that guy. Brown, black, I probably will use this one. And I have a brown, I have an orange, orange. I'm not going to use that guy, but I will use this one. And yeah, what the heck, I'll go ahead and use this one. So what I'm going to build for us will look like this, based on these resistors that I have. So this will be a focus. All right, the circuit will look like this. We will have power. We will have a singular resistor. we will have a point A, we will have a point B, we will have this guy coming down to here, we'll have another resistor coming out this way, like so. How about that? And we'll call this R1, we'll call this R2, we'll call this R3. And of these three resistors, I'm going to make this one 100 ohms. I'm going to make this one 180 ohms. And I'm going to make this one 120 ohms. And so here, remember, when we're doing circuit series parallel analysis, we have to do some circuit redraws, yeah? So to simplify what's happening in here, we said we're going to use our red pen. Everybody's going to bring in red pen for marking polarities, yes? And isn't that how we mark the polarities for our voltage source? How will the electron current flow? Robert, which way will the electrons leave the source? Roberto.
From positive to negative.
The electrons will leave. Which plate of the source do the electrons leave? Electrons.
From the negative source.
Yeah, electrons are negatively charged, so they will leave the negative plate, flow down, bend the corner like this, and then it hits this node. What happens when the current hits this node? Wei G. What happens when the current hits this node? Wei G, are you with us? Yusuf.
It goes split and then.
Okay, it splits. Part of it will come up through the R2 resistor, yeah. The other part will happily continue and then come up through the R3 resistor, yeah. So the current will split. What happens at the top? The current that comes this way will bend around and then join with this current that comes up through R2. What happens at node A is these two currents will combine to go through R1 in that fashion. Everybody get a sense of how the current flows in the schematic? So far, so good? All right. So based on this, seeing the voltage source, seeing how the current's going to flow, we said we want to start our analysis of series parallel reduction. We call this, we're reducing the circuit, we're simplifying the circuit. So we start at a point farthest away from the voltage source. So let's say we put our eyeball right there. There's you, and you're looking at the circuit from that perspective. And as you look at the circuit from that perspective, you see a wire. On that wire, you see R3. R3 is attached to point B, and R3 is attached to point A. What is its relationship to the resistor closest to it? Jacqueline?
It is parallel.
Okay, which one is in parallel with which?
R2 is in parallel with R3.
Okay, is everybody in agreement? R2 is in parallel with R3? And since we're simplifying, we're looking for the easiest things that we can group to simplify, then maybe in our redraw, we want to show these two guys combined. So in my redraw, which is directly underneath the original one, I'm going to put my voltage source like so. I'm going to have my first resistor. Here's my point A. So here's my R1. This is still 100 ohms. That hasn't changed. And here is my point B. However, what I have between point A and B now is a combination of these two guys. These have been simplified and combined into a single. And how should I label this? Wei G, do you remember how I should label this? This is called R what?
Equivalent resistance.
It's an equivalent resistance, so it's E
Q
number
1.
Okay, because in more complex circuits, I may have REQ2, REQ3, REQ4. So I'm going to label this REQ1. And this is, as Jacqueline said, R2 in parallel with R3, yes? Okay, so that's my equation for this resistor. So how does this calculate? This calculates to be 180 ohms in parallel with 120 ohms. So how do I key this into my calculator? My REQ1 is equal to, How does the keying work into my calculator? Isn't that 180? And I hit what key? My reciprocal key, yeah? And then hit plus. And then I hit my 120 and hit my reciprocal key. And then hit equals. And at the end of that sequence, I have to hit reciprocal one more time. And I have to hit equals one more time. So do that calculation for me, everybody. What is my REQ1 going to end up to become? Question goes to Robert. Can you do that calculation for us, please?
I got 72 ohms.
72 ohms, cool. How many people agree with 72 ohms? Raise your hands. Yay, all right, 72 ohms. Is 72 even? No decimal points or anything?
Yeah, no decimal points, just 72.
72 omegas right there. Cool. All right. So now we have a value, 72 ohms, and we can go ahead and write that down, 72 ohms. So my voltage source that we're playing with is 5 volts, And so now I've taken a 3 resistor series parallel circuit and reduced it from 3 resistors to now a 2 resistor circuit. And guess what? In doing so, I end up with a simple series circuit. How do I determine my R total? What is RT? RT is equal to what, Jacqueline? A formula.
It is equal to R1 plus REQ1.
R1 plus REQ1. Exactly. Those are the 2 elements that I have in series, yes? And that is the equation that comes about based on the simple series circuit. Do I have the ohms of R1? Do I have the ohms of REQ1? It's 100 ohms plus 72 ohms. So my total should work out to be, raise my camera up. My R total should work out to be 172 ohms, yes? Is everybody confident about that? Feeling good about that? Okay. Now, one more thing we ought to do, and that is to practice writing a singular equation for all the original resistors for R total. Okay. How do I write a singular equation for R total? RT equals, what do I write down? Wei Ji?
R1 plus R2 parallel in R3.
Like this?
Yes.
Okay. I would caution everybody to do one more thing. When we go to write these equations, let me make this camera just a little higher so we can see more of the paper. All right. I would caution everybody to do one more thing, and that is right here. I would caution everybody, let's put in parentheses, okay? Because we want to distinguish this parallel relationship as being a separate group from R1. If we don't put the parentheses here and we just read this straight across, is it conceivable somebody would have done R1 plus R2 first and then put that sum in parallel with R3? It's entirely possible. We don't want them to read this straight across without having the parentheses in place. Does this help everybody understand a little more clearly that this is a better way of writing the equation? Okay, okay. So this is your R total equation. Now, we're going to build this puppy, and let's see, let's go ahead. We wanted a 100 ohm resistor, and so we have a 100 ohm resistor. So I'm going to do my 100 ohm resistor right here, let's say, okay? And I have a 180 ohm resistor, so I'm going to put a 180 ohm resistor right here to here, let's say. Let's do this on to number 20. Let's make this nice. Go to number 20 right there. And I'm going to insert a couple of these jumpers because I want to maintain my parallel relationship. and put 120 here. So there's the 120 ohm resistor. Nice. And I want to bring in my power connections. So I like to use yellow. So I'm going to bring this in for my power connection, right to there. And I'm going to bring another couple of yellows for paths going to ground. So here's another one here. So this will be a connection for this resistor going to ground. And another one about here for this to go to ground. Okay. And let's look at this closely. Bring this guy right down here and hit focus. Boom. Do I have a 100 ohm resistor connected to the positive side of the power source to some row? In this case, it's row 26, looks like. And the other side of the resistor is connected to a connection point with this jumper to two other resistors. And these two resistors are set to be in parallel with each other going to the negative side of my power source. So it shows this resistor, the 180 ohm resistor, sharing a common node with the 120 ohm resistor through the green jumper wire. So they are connected at the top, and they are connected at the bottom to my blue rail down here. And the reason I want to do this way is I'm going to show you how we're going to measure branch currents in here as well. So all this looks pretty good. Yes, so is everybody in agreement the circuit is a representation of our circuit boards? Schematic. So far so good? Okay, okay. I'm going to pause for a moment. All right, now that I have the meter back with me, let's go ahead and confirm our resistor values as being the right values and also in the correct position. Pardon me. All of these happen to be under 200 ohms, so I'm going to use the 200 ohm scale. And when I'm making my resistance measurements, what I need to do is to isolate the resistors. So I'm going to yank this jumper wire for now to remove the parallel relationship between these resistors. And I'm also going to remove the power supply board so that the circuitry of the power supply is not influencing any of my ohmic measurements. So now each resistor is completely isolated. First thing to do is to make sure my leads are working properly. My continuity test. So that's good. Go to the 200 ohm scale. I expect something close to, pardon me, 100 ohms here. Let's go ahead and test this guy. Stab and stab. Ooh. Pretty good, eh? 100.0 or 100.1, somewhere in there. That's close enough to 100 ohms. So did I verify this is 100 ohms and it's in the right place per the schematic? Next one should be 180 in my R2 position. So I'm going to go ahead and stab and stab. Pretty close to my 180, 179 point something is a really good fraction. I will go with that. And the last one should be something close to 120 ohms in my R3 position. This is my R3 position. Let's double check. And there's close to 120 ohms. So are we happy we've selected the right resistors? And are we happy we put the resistors in the appropriate places in our breadboard that mimics our circuit? Our schematic, yes. And let's go ahead and pop this guy back in. Okay, now we calculated an R total, yeah? We calculated an R total, we made two calculations. We calculated an REQ. Can I verify the REQ for that pair of resistors? Sure can. And let's go ahead and do that. Back to my ohm meter mode. I've put the jumper back to make those in parallel with each other. So if I go to connect from the blue rail to either this resistor or this resistor, I should get the REQ for this pair of parallel resistors. And we said REQ should be about 72 ohms. Higher so you can see a little better. How's that? Okay, we said REQ should be 72 ohms. Let's go ahead and double check and see by stabbing here and stabbing over to here. Do I get my 72 ohms? Wow, look at that. Pretty close to 72, 71 and a fraction. I'll go with that all day long. And how about if I change my measuring point? Suppose I go to the top of the singular resistor. I'm only measuring across R2, but yet it's giving me the equivalent resistance of the pair of resistors in parallel. Why? Because they are connected with the green jumper wire, and they are connected to the blue bus down below. So whether I do this or whether I do this over to here across the R3 resistor, I'm still going to get their equivalent resistance in parallel. How about the R total? We had an R total that we calculated to be 172 ohms, yeah? And so for 172 ohms, how would I measure the total ohms here? I would measure this from the red power rail all the way down to the blue power rail. How about that? So we'll go ahead and do that. I will hook up to the red power rail on the top and hook up to the blue power rail at the bottom. And does my meter show me something close to 172 ohms? Pretty darn good. We're happy with all that, yes? So far, have our calculations been borne out by our circuit board measurements? Yep. Now, a couple of the things we're going to do. Turn off the device when we're not using it. All right, so we're going to need to do a VIR chart for this, yeah? Well, let's go ahead and put together a VIR chart. VIR. And for R1, for R2, for R3, and totals. And for R1, this was 100 ohms. For R2 was 180 ohms. For R3 was 120 ohms. For the total, we calculated 172 ohms. The total voltage is 5 volts. And we've calculated this more than once. We've measured it. We're happy with 172 ohms. What would be the next thing we would do to complete filling in this table? Robert Benavides.
Find current.
Okay, and how would I find current? What method would I use? Robert?
Ohm's law.
Ohm's law, which I wrote up here, Ohm's law. All right, so in order for me to calculate the I have a V over R. Do I have a V over R here?
Yeah, Ohm's.
So let's go ahead and do that. Everybody pull out your calculators and take 5 divided by 172 and hit engineering. And your calculated result, Yusuf, what do you calculate?
29.07 watts.
Watts?
Yes.
Current is measured in watts. Power is measured in watts. Current is measured in amps. Okay. So 29.07 milliamps. Got to know difference between watts and amps. Watts won't kill you. Amps will kill you. All right. So 29.07 milliamps. And that was a pretty quick calculation. We want to, before we fill in that, well, you can't just fill this in because it's not all series, but let's go ahead and fill in what we can. Let's go ahead and double check this value. Clear, 5 divide by 172. It's a 3-second calculation. In engineering, are we in agreement? This is 29.07 milliamps. Everybody's okay with that? Put a double check mark because we've checked that. We're happy. So in our schematic, you have a positive, you have a negative, and the current flows down, and it flows here, and it flows here. It flows up, and it flows back to the source. And I have 29.07 milliamps flowing in this circuit. I also can take this information up here, right here. I have 29.07 milliamps flowing to this node. And I also have 29.7 milliamps coming back to the source. Well, guess what? Once I calculated this current, which is iTotal is equal to 5 volts over 172 ohms, is equal to 29.07 milliamps. Once I calculate this current, I realize, doesn't this current flow through one of my original circuit resistors? This original circuit resistor carries the total current. So do I need to calculate anything for IR1, or can I just simply write this value based on a simple series circuit that IT is also IR1? Are we in agreement this iTotal is in fact the current that flows through one of my original circuit resistors? And I can fill this in right here. So it is 29.07 milliamps. Done deal. Is it also the same current that flows through each of these? Does this 29.07 milliamps flow through R2 and R3? It flows through the equivalent. Does the same value flow through each of these? The question goes to Yusuf.
They're divided, so no.
It divides. It splits. We saw over here it splits. Some of it goes here, some of it goes here. Which which branch will have the highest current? Jacqueline, which branch will have the highest current?
R2,
R2 will have the higher current, and why will it have the higher current?
because it has the higher ohmic value.
Well, it would have in a parallel circuit, the higher ohmic branch, because there's more resistance, more restriction, will have less current than the branch that has lower ohms. This has lower resistance to current. So as this has lower resistance to current, it should have more conduction, more current flow through it. This is a higher ohms. It should have less current flowing through this. So if we recall back to our summary sheet, and our summary sheet said for parallel circuits, right here for parallel circuits, says the largest ohmic branch will have the lowest current. And it says the smallest ohmic branch will have the largest current. So that's from our summary sheet. And so if we compare these two, of these two, this is the larger ohmic branch. It should have less current. Okay, what you're thinking about, and we need to clarify this now, is from up here in the series circuit, the larger ohmic resistance will have the largest voltage. That's where largest and largest go together, is when they're in series, all right? But when they're in parallel, the largest ohmic branch will have the lowest current. So in parallel, that relationship is opposite. So let's see what happens here. How do I determine how much current flows in each of these? Well, there's two ways to do this. One way is to do current divider formula, and we can review current divider formula. Our famous CDF, current divider formula. And current divider formula, if you recall, had a general form where it was IRX is equal to RT over RX times I total. If I want the current through R2, it would be IR2 is equal to something over something times I total. How do I set up my numerator and my denominator? My numerator says RT, my denominator says RX. If I want R2, doesn't R2 go in the denominator? What do I use for RT in this particular case? ESYS. Okay, so my question to everybody, let me reiterate this. My question is, current divider formula is written generally as IRX is equal to RT over RX times IT. If X meaning the unknown resistor. So if I want the current through R2, then the value of R2 goes in the denominator. My question is, what value do I use for RT? Do I use the RT for the circuit? Or do I use the R equivalent for the bank? Yusuf.
I guess I would use the RT for the circuit.
Well, current divider formula is only for parallel. Current divider formula is only for parallel, just like voltage divider formula was for series. Well, the only part, the whole circuit is not parallel. The only part that's parallel, these two guys. So we wouldn't use RT for the whole circuit. We only use RT for what's in parallel. And what's in parallel was called REQ1. These two guys in parallel gives us REQ1. So this is RT for the bank. And what's bank? Bank is the nickname for parallel resistors. So I have a pair of resistors in the bank, and the R total for that bank is called REQ1, not RT, but we will use this value for this part of the formula. So this is REQ1. Okay? So we have to get our terms straight before we throw in numbers. Now we'll go ahead and throw in numbers. So the REQ1 was 72 over R2, which is 180, and multiply this by my 29.07 milliamps. Everybody make that calculation right now. 72 divided by 180, multiplied by 29.07, and don't forget, this is milli. So you key this in as 10 exponent negative 3. So on the calculator, turn this guy on. On is this button. It will be 72 divided by 180 times 29.07 milli is exponent negative 3. And when I hit equals, what value do you calculate, Wei Ji?
11.63 milliamps.
Okay, and we look in the calculator, we can see 11.628, that 8 makes us round this to become 11.63, and you see 10 negative 3, so it's milli. And so yes, we should be happy we have 11.63 milliamps. How many people concur? Raise your hands. Wave at me. Jacqueline, you're not waving? Oh, you are waving, okay. I'd be concerned if you had a different value, all right? Or if we were wrong. All right, so that worked out to be 11.63 milliamps. Now we're going to calculate IR3. So if I'm going to calculate IR3 based on this general formula, again, it will be REQ1 over R3 times I total. And in this case, it's still going to be 72 over, in this case, 72 over what? 120 ohms. 120 times 29.07 milliamps. So IR3 works out to be what value? Robert, do you have this calculation for us?
17.44 milliamps.
I believe you. I need to do my calculation to keep up with you. You guys are so fast. 29.07, -3. So you said 17 and change?
Yes.
And yes, 17.44 milliamps. Cool. 17.44 milliamps. We'll write down 17.44 milliamps. How do we know this value and this value are in fact correct? How do we know the IR2 and the IR3 are in fact correct? Well, if we take the information back up, does the 11.63 milliamps here and does the 17.44 milliamps here, do these flow together and add back up to 29.07 milliamps going back to the source? And if you go to add these two numbers together, guess what? They add up perfectly, okay? So are we happy with the currents as we've calculated them? They're correct in value. Now, the other thing you want to double check is the correct current in the correct branch? So back to you, Jacqueline. Higher ohms, less current, yeah? Lower ohms, more current, yes? Okay, are we good with that concept? Good, okay. Now, the last thing to determine will be these voltages, and now that's just simple math, right? We just take the I times the R is equal to the V. So let's go ahead and punch those guys out. Jacqueline, you do VR1. Yusuf, you do VR2. Wei-Ji, you do VR3. All right, so Jacqueline, 29.07 here times. Jacqueline, what is your VR1, please?
2.91 volts.
2.91 volts. That is correct. And Yusuf, I believe I asked you for the next one. What is VR2, my friend?
Sorry, I did the math wrong. It's
11.63 milliamps times 180.
2.09 volts.
2.09 volts. And Wei-Ji, what do you have for VR3?
2.09 volts.
2.09 volts. Oh, my friends, look at my paper. Could this be possible? Did we have a mistake somewhere? Is this coincidental or is it meant to be? I have this current times these ohms. This current times these ohms giving me 2.09. I have a different current times different ohms, but it still gives me 2.09. Is that possible? Yes or no? Why is it possible?
Because they're parallel.
Because in a parallel circuit, back to our summary, what is the same? Item number 3, voltage is the same across all branches of a parallel circuit. From our summary statement, voltage is the same. Well, here's a branch and here's a branch. The voltage across R2 must be the same as the voltage across R3. That's why these two guys have to be the same. Woo-hoo. Now we have done a series parallel circuit reduction by redrawing and simplifying. We've reduced 3 resistors down to 2. These 2 in parallel gave us R equivalent number 1, 72 ohms. These 2 in series gave us an R total of 172 ohms. We have an equation for R total. We transfer all of this into a VIR chart, do the math, find the total current. We discovered that total current flowed through one of the original circuit resistors, which allows us to fill this number in for IR1. We discover by taking this information into this schematic that the current 29.07 milliamps, the total current splits. So we have to do a current divider to figure out how much goes into each branch. We did that using current divider formula and discovered our branch currents, wrote those in. We're happy with the lower current in the higher ohm path and the higher current in the lower ohm path. We then filled in our voltages and we seem to be happy with the voltages. The only thing left now is to do our measurements. Boom. Take my circuit board and let's go ahead and wire this puppy in here. There I am. Okay. So what I'm going to make required going into the next semester is that everybody should also acquire one of these really nifty extension cords. So you can have your wall wart plug some distance away, and with an extension cord, something longer than the 12-foot blue cable you got to plug into the power supply. So I'm going to plug this into a power rail. There. All right, yay. And now have this power my board right here. Boop. Turn this guy on. Yes. Okay, let's start verifying some of these items on our VIR chart. Let's go ahead and set this guy up for voltage. So let's go ahead and measure our source voltage first. We expect something close to 5 volts. So I'm going to go power rail here and negative rail here. And does my meter show me something very close to 5 volts? We're happy so far, yeah? We want to measure VR1. So VR1 predicted to be 2.91 volts. And the positive side of this resistor is on the left side. That's the positive side of the resistor. And this goes to the negative side of the resistor. In fact, let me help you out. Bring this down a little closer here. This. Okay, and move all this slightly in this direction. All right, so you can see things a little better. Is that better for everybody? And I'm going to go measure here and here. We expect something close to 2.91. Hey, we get 2.94. I'm happy with that. That's real world. And we want to verify our bank of resistors, 2.09 here, 2.09 here. So I'm going to measure on that point of the resistor and here. Wow, 2.09. And I'm going to measure on this side, measure on this side of the resistor to here. And lo and behold, I get 2.09 on that resistor. And from what we learned before, it doesn't matter whether my red probe goes on this side of the bank or on this side of the bank, as long as I'm making some kind of a measurement, or on this side of the bank down here, as long as one is at the top and one is at the bottom, I am going to get the voltage of the bank, which is 2.09. Now, the current measurements, my friends, here we go. If I want the current that flows through R2, couldn't I just pull this yellow wire here? Because isn't this the current that flows through R2 to the negative rail? So if I do this, yank this one jumper wire, I'm going to leave part of it hanging because I need a connection point. So have I created an open from where the jumper wire was to where the jumper wire is? Now keep in mind, the jumper wire was on this hole, but I'm not making any electrical contact to the strip underneath the board. So what I should do is I should touch the resistor. Is everybody clear on that? I don't touch the hole where the jumper wire was. I have to touch the metal wire of the resistor. And as long as I do so, and I should set this into current, let's go to 20 milliamp scale. I should be able to, from here to here, get something close to my 11.63 milliamps. Okay, I get 11.07. All right, that's real world, because I have some tolerances and other things at play here. Now, if I want to measure the current through the third branch, what do? I have to rebuild this branch. So I rebuild this branch there and yank out this wire right there. And again, how do I make this connection? Let me bring this camera out in this direction so you can see more clearly. And I'll focus. And again, the yellow wire was at this point, but I can't put my probe here because it's not reaching into the hole to the metal strip underneath. I have to put my probe right on the metal of the resistor, and then I put this probe on the metal of the jumper wire that I removed. I expect something close to 17.44 milliamps, and I'm measuring a little low. That's okay. But is this the higher current in the lower ohmic branch? Yes. Was the other one the lower current in the higher ohmic branch? Yes. So you write down what you see. Now, let's go ahead and rebuild this guy. Did we have a total current? The total current calculated to be 29.07 milliamps. Do I have total current flowing through this jumper wire at the top? The answer is yes. So if I go to remove this jumper wire, leave a part of it hanging, so I've got a piece of metal to make contact with. Did I create an open between here and here? That's where the jumper wire was placed. And again, I have to put my red probe closer to the positive side of that open, which goes here. Where does the black probe go? Does the black probe go to where the jumper was? No, it can't, because again, the black probe is not reaching down into the hole where the jumper wire was placed. I have to connect this pin to the resistor. And in doing so, I have to go to the next scale here. There. Expect something close to 29 milliamps, and what do I have? 28.7 milliamps. So all my currents are measuring slightly less, but that's okay. Do we have a total current that is not far away from our calculations? That is correct. Now, how do I measure current for the resistor itself, the R1 resistor? I can do this. I can take my R1, move it to go to the power rail. So my resistor is connected to the power rail. It comes down here, and I have created an open between here and here. Here is my open. This resistor was connected to a junction point to the green jumper wire and these resistors. So I've created an open. So this is specifically the current through this one singular resistor, and we expect something close to 29 milliamps. And again, we get our 28.7, which was our total current from before. So is everybody okay with how to do a complete circuit analysis of a series parallel circuit and all of the complete analysis of a series parallel circuit, all of the calculations, the circuit building, and the measurements of the voltages and currents to validate our calculations. And hopefully that will be how you will be exercising these skills in solving circuit number 14, because that is part of your homework assignment. And I think there's also a 9.5 in there. I will double check my notes. You will see notes on Canvas and Discord regarding that. Any questions for me, my friends?
Some people were saying they couldn't find the circuit build on Canvas.
Circuit build 14 is on Canvas. Let me double check on here. Let me go to Canvas, share screen, and share. Boom. And let the stabilize, stabilizing. Aha. 9.5 VIR circuit analysis is in week 5, and circuit 14 is in week 6. So week 5 shows 9.5, and week 6 will be, I have to change some things on here. I'll make that available, but I will change some things in here because we won't be playing with O-scopes yet. So your circuit 14 is in week 6. And what we will be doing will be the Bobot exercise and some other things. So I will just clear this other stuff, but week 6 is now available to you with some photos in circuit build 14, and then your circuit build 9.5 voltage analysis is here for week 5. And let's take a quick peek to see what that guy looks like. Oh, there's another series parallel. Bingo. All right, and some of you have completed this, and some of you who have not yet, you still have time to complete this. So
And we're changing that one to 5 volts as well, yeah.
Yes, you're changing this to 5 volts as well. Yeah. So 9.5 and circuit 14 will all change to 5 volts. Is everybody okay with this now? Yes, I'm sorry. I know you got to go. Thank you so much. I bid you farewell. Yes.
I might be a little bit late today, I guess.
It's okay.
Yeah.
It's okay. It's okay. It took just a few minutes longer. Anyway, have a lovely evening. We will sign off, and we'll keep in touch through Discord. Adios.